Okay. Hey. So I'm going to go ahead and start running through some of this review with you guys. That way you guys can study with me, and at least you're going to be studying the right stuff, right? So we're going to start with the back, huh? Not right now. But, okay. All right, so we're going to start on the back page, okay? So make sure you're on this side. We're going to start with the concentration calculations, right? So looking at number 22, it says, in terms of concentration, a solution with a large amount of solute in a solvent is what? So are we going to say concentrated for that or diluted for that? Concentrated, okay? And just a reminder of what these words are, solute, solvent, solution. We had in our notes, okay, that we said, okay, whatever we put into something, that is our solute, okay? The stuff that we're putting it into, usually the water, is solvent, and together this makes the solution, right? All right, so knowing that, we're going to say concentrated for our number 22, concentrated. In terms of concentration, a solution with a small amount of solute, okay, so less stuff being diluted in there, that one's going to be more solvent, so we're going to say we diluted it, dilute, okay? So when we had that discussion about, Gatorade or any of our Kool-Aids that we mix on our own, if we water it down, that's diluted, more solvent. If we put less water or we usually just add more of the sugar stuff, then we have concentrated. And that's usually the ones that are super sweet. All right. Number 24 said, if you have a 3-liter solution that contains 45 grams of sucrose, what is the solution's molarity? So when you're doing this one, okay, and this one there is going to be one question like this on the test. This is the one where we had to do an extra step, all right? But I do provide you with the molar mass, which is a good thing. The molar mass for sucrose on this should be 342.297 grams. So we'll round it to 0.3. We'll just say 0.3. That'll be easier. Grams, okay? So the molar mass was this. And the way I got that molar mass was I used my periodic table, but I will provide you with the molar mass so you don't have to worry about looking for that stuff, okay? Then we're going to take this grams, and we're going to convert our grams into, do you guys remember? Here's our little triangle for the molarity calculation. So we have molarity, big M, is equal to moles divided by liters, or volume, right? So looking at this triangle, what is the thing that we're going to be using that grams to get? Moles, exactly, all right? So remember, this is the extra step every once in a while. If we provide it to you in grams, you've got to get it to moles before you do any of the dividing, all right? Otherwise, be ready to use your triangle. Remember, you're going to cover up whatever you're solving for. So if I give you a question where I'm asking for, instead of molarity, which is what we're going to be doing right now, moles divided by liters, if I say, hey, we're going to be solving for moles, you're going to cover up the word moles, and you're left with molarity times liters, okay? You guys had, you might have gotten it back just now, one of the assignments where you got to practice your dilution calculations and the molarity calculations. That's a good one to look at if you're still needing assistance or more practice. All right, so continuing on with this, we're going to start with our 45 grams. So this is for number 24. Okay, I'm going to have my 45 grams. I'm going to do times in a line. I'm going to have my 1 mole of it is equal to the molar mass, which is 342.3 grams. So I'm dividing by that. Remember, this is over 1, so you're basically multiplying 2 of these fractions, okay, which is, since they're diagonal from each other, you can just divide them. So when we divide those two numbers, we should be getting a value of whatever I get. So I have 45 divided by 342.3. So I got 0.131. 0.131 moles. Okay. Once I have moles, I'm good to go. I have moles down here, and I had liters up here in the problem itself. I'm solving for molarity. Okay, so molarity was equal to moles divided by liters. So when I plug and chug into that, I'm going to have 0.131, and I'm going to divide it by 3.0. So I'm going to put that into my calculator. 0.131 divided by 3.0, and I get the answer 0.436. I'm going to round up to 0.44. 0.044, sorry. Okay, now remember this extra step, I'm going to provide you with the molar mass, so just make sure that you're making sure that it's in moles first. If I have time, I'll change the question to just be giving you the moles, so just be ready to use the triangle, okay, and calculate it that way, but just in case, this is that extra step, all right, and I'll put a reminder on the board to divide. Any questions on 24? All good so far? All right. Number 25. Actually, I'll use this space down here. All right, so number 25, reading this question, it says a beaker contains 0.1 liters of 12 molar solution of HCl. What would its new molarity be if you added water to it to make the volume 300 milliliters? So the first thing that I'm going to point out, you guys don't have to be worried about this. I made sure on the test that they're going to be the same unit, but always double check it. It's always helpful. So I think the one that would make most sense to us is making sure they're in milliliters. So we're going to take this 0.100 liters. What is that in milliliters? Does anybody remember? 100, exactly. So this is 100 milliliters. All we did was move that decimal 3 to the right. So we have 3 pieces of information. That should tell you that you're not using this triangle. You are using the dilution formula, which is M1 V1 equals M2 V2. Anytime we're saying what is the new molarity, that's a good indicator of that, okay? So we're just going to match these up just like we did in our little Schoology assignment, where you're just going to put the numbers straight with them. So I have 12 molar is M1 times V1, which is going to be 100. I'm going to set that equal to, we need the new molarity, so I'm going to leave that M2 times, and then V2 is going to be this 300 milliliters. So once again, we're just lining them up. The way that we decided as a class that we were going to be solving this, we're going to simplify the side that doesn't have any variable. What I mean by variable is any letter, right? So I'm going to take my 12, I'm going to multiply that by 100, and I get 1,200. So I'm going to go ahead and write that number down. I'm going to say is equal to, and then we have M2 times 300. So with that, we know to move this one away from our variable. This one we got to leave alone. So we're going to divide both sides by this 300. And what that does is this side will cancel out, and then we have 1,200 divided by 300. To get our answer of 4. So our new molarity, or M2, is going to be equal to 4 big M. And if you had moved both of them to be liters, like they're both decimals to start with, the ratio is still the same, so you would have still gotten the same answer. That's the cool thing about it. All right. Any questions on this? This is the one I think that people struggled with the most, just knowing to multiply together and then divide away. Multiply together, divide away, all right? And that's kind of always going to be the setup. And make sure that you're putting the numbers together that are talking about the same substance, okay? All right. Any questions? Ready to move on? Ready? All right, let's go ahead and look at the solubility graph that was right at the top of the page, okay? So a couple things to point out on this graph. So on this graph, we notice all of these lines are increasing, right? So not part of the review, but if I were to have asked you or said something like, one of these looks like they stay pretty constant with increasing temperature, which one would you have told me? So if I were to ask you about stays constant, the solubility with increasing temperature, which one is it? Which one? NaCl. Is that what you said? I'm sorry. Okay, so NaCl is the one that's kind of gradually going up. All right. But it's like not a lot. So it stays pretty constant. So NaCl. So when I'm saying it doesn't change its solubility, remember each of these curves is the solubility of these, right? Okay, the other one that isn't on here, but I'd like us to kind of draw it in there so you have it to study a little bit later. If we had a solubility curve that looked like this, okay, and we'll go ahead and label that as NH3. So if I had one that was decreasing, what would this be evidence of? So you may remember. It was a state of matter. You're thinking sodas, hot sodas, huh? A gas, okay? So gas will decrease in solubility. They are the only ones, all right? This one I would study that statement. You will see that question. And that was one that we kind of covered a few times. Every single one of our curves has had a gas. I don't know why we chose not to give you one on this one, but we didn't. So so I would draw yourself a little line and just remind yourself that gases, you're thinking hot sodas. Everything else, you're thinking, how would you try to dissolve sugar? Okay, the way that you want to do that, increase temperature, increase stirring, make pieces really tiny. We'll talk about that in a second. All right. Now, the rest of these questions, let's go through it. So we're going to start at number 18. It says, at what temperature are the solubilities of NaCl and KNO3 equal? So when we're trying to figure out if the solubilities are equal, what are we actually looking for? What's going to be evident? Where they cross. Yep. So where they cross. So I'm going to say where cross. All right. So NaCl, and remember, I'll make it available to you if you wanted to use a highlighter tomorrow or a ruler. It's also helpful. Both of those things some people have really gotten used to using. But NaCl was this one going like that, and then KNO3. I'll do in orange. Is kind of going up the way. So we're looking where these two crossed, which was right about here. Okay. So at what temperature? So is temperature on my x-axis or my y-axis? X. Good. So we're going to look right there. We're going to kind of shimmy on down there, and it's about right here. So you got to figure out how this goes, right? So we see 20, we see 40. In between those two, this would be 30. So it's in between 25 and 30. So a fair answer would be maybe, what would you guys say? 26, 27. Yep. So I'm going to put 27 degrees Celsius. And that's a pretty fair answer. All right. Number 19. 19 says at 90 degrees Celsius, so this is on our x-axis again. Okay. What mass of KBr will be soluble in 100 grams of water? Do we care about the 100 grams of water? No, we're going to ignore that because that just means, that's just telling me what graph I'm looking at. So just ignore that number, okay? But the mass of KBr, we're going to be reading off of our y-axis. So we're going to look over 90 degrees Celsius. We're going to find that line. So you had to think a little extra. So this would be 80, 85, 90. So this right here is 95 or 90. Sorry, going all the way up. And then I'm looking at where KBr hits that. So we're going to look right here. This is where having a roller might be helpful. And I'm going to look across right here. And we are really, really close to the 100. Not necessarily on it, though. We're like right below it. Right? So What would you guys say for that? About 98 grams? Yeah, 98 to 100 grams. So. Okay, so again, you saw me use the ruler. I really do recommend it. I do have other ones, so if you need one tomorrow, definitely ask me. Number 20 says, if a solution contains 120 grams of sodium chlorate, so we have, this is our y-axis. We're going to read up the side. At 20 degrees Celsius, that's my x-axis, so I'm going to look at those. When I give you two numbers, I would definitely just find the point, make a mark, and then figure out where your graph is, okay? So we're going to pay attention to 120 grams. So I'm going to go up. 120 is up here. I'm going to go across to 20 degrees Celsius, which is right here. So I'm going to kind of make these two meet. So I'm stopping right about here. I'm going to make a point on my graph. And then I'm going to figure out who they're talking about. They said NaClO3. So that one is this crazy one kind of going up the page. It might have gotten cut off on yours, sorry. But according to this, where does the dot lie? Above it, on it, or below it? It's above it. So what would we call that? Super saturated. All right, so I want to make a big point on this one again because there are quite a few individuals who are getting confused with what you're actually saying is above, below, or on. Remember, the dot is our new conditions. This is what we're analyzing. And we're saying, okay, in relation to what the original solubility was, where are we now, right? So you're looking at where the dot is in comparison to the line, not where the line is in comparison to you. Okay, you're always looking at the dot that it's talking about. So just make sure, tomorrow put a dot where you're talking about, and that way I can at least credit you for knowing where you were, what you meant. All right, but try to remember that the dot in relation to the line, not the line in relation to the dot. All right, last one said, which solution is least soluble at 20 degrees Celsius? All right. So you got to be ready to see the word least or most. So a reminder, least soluble will be the lowest number or the lowest point. I'm about to lose all my lead. Okay, there we go. So lowest and most would be highest. So we're going to look at 20 degrees Celsius. We're going to analyze that line. So 20 degrees Celsius, I'm just going to look all the way up. Okay, and then I'm going to find these different lines on the graph. So NaClO3, looking at 20 degrees Celsius, is way up here. KNO3 is going to be right down here. So far, this one, not that. NaCl is going to be right above that KNO3. Okay, so we're going to say, nope, this one's still our winner. And then KBr is way up here, so can't be that one either. It's going to be KNO3 as the lowest or the least soluble. Okay, so hopefully that kind of helps a little bit. Please notice that you take your time on those questions. Don't just rush and think that you can just do it like with one finger. Like use your hands, use your highlighters, your rulers, whatever you got to do. All right, are there any questions that I can assist with on that one? All good? All right, let's flip the page. Okay. So this is still having to do with solubility curves, so let's hit that one up right now. What we see on number 14, it says a supersaturated solution. So super contains, the answer is more than the maximum amount of solute. Because remember, your maximum amount of solute is where you reach saturation. So make sure you remember, if you are supersaturated, what's going to happen as you continue to add more solute? If you're supersaturated, does anybody remember the thing that I walked around, the little hot pack? If we agitate it, what happened? It all solidified, right? Everything came out of solution. So if you go above and be like above where you are at supersaturation, that one's going to completely take everything out. But more importantly, if you reach saturation, anything you add is going to settle down to the bottom. It's not going to dissolve anymore, okay? All right. I also added in, how do you make a supersaturated solution? So remember, this was sweet tea. So what was our discussion on that with a supersaturated solution? We have some sort of a solubility curve, right? Here's our grams, here's our temperature. What are we going to do for supersaturated? What's the first step? Excuse me. Heat it up, exactly. So we're going to basically heat this solution up. Okay, so first step, heat up. What are we going to do right when we get to this temperature? Think about that sweet tea. We're trying to add sugar to it, right? So we're going to add until saturation. So we're going to add solute until we hit that solubility curve, the saturation. So add solute. Okay. Then we're going to cool it down. That's our last step. And then once you've done that, now you have something that is above your curve, right? Heat it up, add your solute, cool it down. It's a process. You guys kind of remember talking about that a little bit? For the most part. All right. Number 15. Let's look at number 15. So number 15 says a saturated solution contains blank the maximum amount of solute at a certain temperature. So saturated. How would you explain that? We already said more than the maximum. So what was it here? Equal. Yep. Equal to the maximum. So saturation is equal to the maximum. It's the one that's on the line. This means that as you add more solute, it will not dissolve. Okay, now this isn't supersaturated where it's going to agitate it and bring everything out of solution. This is the one where it's not going to dissolve, it's just going to settle down to the bottom. Okay. And then finally, an unsaturated solution contains, what do we want to say for that one? We have more, equal to, less. Yep, less than. The maximum amount. This means that as I add more solute to an unsaturated solution, it will continue to dissolve as long as you are doing the methods needed for it to dissolve, like stirring it. So it will dissolve. Oh, we can't see that. Sorry. It will dissolve. All right. And then number 17, we kind of already used these words on at least one of the questions. So labeling the following as unsaturated, saturated, or supersaturated. So the first graph that we have a star that's above the line. So which one is that one? Supersaturated, good. Okay, this one is below the line. So what is that one? Unsaturated. And then finally our last example is right on the line. So that will be saturated. okay? So I'll give you guys a second to kind of fill in any blanks that you still needed. Does anybody have any questions so far on either side? Right. No questions so far? We're all good? Okay. All right. So right above this, we have solubility rules. All right. So we're going to start with the big long list and looking at those solubility rules. You do have this on here. I know it's super tiny. So if you still have your notes, I would have those out to kind of help you if you need it a little bit bigger. Otherwise, it is on the inside of my periodic tables, the blue ones. But what you can add to at least your review, and I will go try to make copies of the ones that I gave you that said aqueous in this corner, solid over here, and then solid right here, and aqueous right here, right? Because that was kind of the way that we trained ourselves, is we were matching up the words soluble with aqueous, meaning it's dissolvable, okay? And then solid with insoluble, okay? So this is insoluble. And then down here, insoluble with solid, and aqueous with soluble, okay? So remember, the way that you're doing this is you're looking at the second thing listed. So look at anion first. So it's the ones with the negative charge. Look at the second thing listed. Find it on your list. You're going to read the sentence out loud to yourself saying, this is soluble unless it's with, and then you read what you have, okay? So our first example we have is we have CH3COO. So looking at this anion, this one matches up to the first one listed, which is our acetate ion. So we're saying that acetates are soluble or aqueous unless it's with, and we notice there are no exceptions to that rule. So we're going to go ahead and say this is soluble, which is aqueous, right? You guys, a number of you guys, I gave back that practice page as well, so that one is worth taking a look at to just make sure you understood it. All right, the next one we have is hydroxides. Again, notice I am looking at the second thing listed always, all right? So the second thing listed for this one was OH, or hydroxide, so I'm going to look down my list right here. Hydroxide is down here. So hydroxides were insoluble, or solid, right? Unless it's with NH4, an alkali metal, or CaSrBa. So looking here, it's with Na. Na is part of our alkali metal. So you might give yourself also the reminder that an alkali metal is what group on the periodic table? Group 1. Yep. So group 1s. And those we wrote out, right? So your group 1 or your group 1 cations was lithium, sodium, potassium, all of those guys. All right. So this one is with a group 1. It's with sodium, so this will make it soluble or aqueous. All right. The next one we have, we're looking at nitrate, NO3. So we're going to find nitrate on our list. Nitrate is up here at the top. So nitrates are aqueous or soluble unless it's with, and we see that there is no exception to that rule. So it's going to be soluble again. Does anyone have any questions so far with those? Okay. All right. The next one, you gotta be careful. It says sulfate. So we know sulfates are soluble or aqueous unless it's with strontium, barium, lead, or mercury. This one is with barium. So because it has this part, because it has Ba, that just changed us to be this, insoluble, which is a solid. So if this was to show up in a equation, a balanced equation, that would be our precipitate. Okay, we'll bring up that word again in a second. But precipitate. All right, number 5 was silver bromide. So we're going to look up the bromine part. So Br, here it is right here. Bromines are soluble or aqueous unless it's with silver, lead, or mercury. It is with silver. So once again, because it has that silver component, that made it insoluble or solid. All right, zinc chloride. Zinc chloride. So we're going to look down our list for chlorides. Chlorides are mostly soluble, so they're soluble unless it's with silver, lead, or mercury. This one is with zinc. Because it's with zinc, that's not one of these 3. That will now be soluble. Or aqueous, okay? Aluminum sulfide. So we're going to look up sulfide. Sulfide is down here at the bottom. Sulfides are solid or insoluble unless it's with NH4, a group 1, or CaSRBA. This one is with aluminum. That's not any of these exceptions. So this one will be insoluble. Okay, the next one we have was SO4 or sulfate. So I'm going to look down my list for sulfate. Sulfates are soluble, aqueous, unless it's with strontium, barium, lead, or mercury. So it's not with any of our exceptions. So therefore, this remains soluble or aqueous. All right, precipitate. What are we going to put for that one? Insoluble. Because it's a solid. And then finally, aqueous is going to be soluble. Excuse me. All right. Number 13, you kind of need a little tiny bit of space. Well, actually, I'll be able to write mine right here. You probably will too. You'll be fine. All right, so a precipitate is produced in a reaction between AgNO3 and NaCl. Although I'm not going to be asking you to put cations together or rearrange things, I am going to ask you this second part of the question and ask you who your precipitate is. So we're going to go ahead and put these together the way that we have practiced in the past. Remember, this cation had a +1 charge. This one had a -1. Sodium is a group 1, so it's a +1, -1. So if we were to put these together, so AgNO3 plus sodium chloride, okay, and I were to rearrange it so that now we have our products, what type of reaction is this? Just looking at my reactants, what type of reaction is it going to be? You got synthesis, decomposition, single replacement, or a double replacement. Who remembers? Double, thank you. Straight from the lab, you guys. That was one of your first questions on the lab. Is a double replacement. So we're going to switch these guys out. Once again, I'm not going to ask you guys to do that part, but I will ask you to remember what type of reaction it is. So make sure you study. Okay, so those are my products. So now that I have everything here, which one is the precipitate? You can already assume it's not one of your reactants, but you can look at your 2 products and check your solubility rules. we have a nitrate with sodium, or we have a chlorine with silver. Which one of those two is going to be our precipitate? Any ideas? It is silver chloride, yep. Because nitrates are on our list as having no exceptions, and they are always soluble. Chlorides have the exception that if it's with silver, lead, or mercury, it turns into being insoluble. So AgCl is the precipitate, okay? And it is a double replacement reaction. That's how we form any precipitate. So, sorry. Is it has to be a double replacement reaction. Okay. So we're kind of coming close to the end. So I'm going to kind of run through these a little bit quicker right now. And then the rest you'll just have to check online for the answers. Okay. So rate of dissolving. This one was briefly went over in our notes on day 1 of this chapter. You had to kind of look for it. So just in case you didn't see it, the 3 ways to increase the rate of dissolution, how you dissolve something. You want to increase temperature. Increase temperature. You want to increase your surface area. And I'll talk about that one in a second. And you want to stir or agitate it. Okay? I don't think we need to go over number 10. You just need to know that these are opposites. Opposite of above, right? So, number 11 says, what effect does increasing the surface area have on the rate of dissolution? So when we are talking about increasing the surface area, I'm just going to show you the image that I drew earlier. It takes me a long time to draw a bunch of little square cubes. All right, so here is the picture that I showed earlier. So if you think about a cube, it has 6 sides to it, right? So 1, 2, 3, 4, 5, 6. Any dice has 6 sides on it, right? So if it has 6 sides, if you were to, and I'm talking about something like a sugar cube, if you were to just drop that into water and say, okay, dissolve, it wouldn't do it, all right? It would take forever. It's not going to do it. So you would want to break it apart into little pieces of sugar, because if you do that, you've now created 1, 2, 3, 4, 5, 6 different pieces. Each of them have 6 sides. So now we've just done 6 times 6. So we went from having 6 sides to a total of 36 sides. So when we crush it, when we grind things to make them smaller pieces, I think we've all had that experience where you're trying to make Kool-Aid and you've got a little bit of water in the container and it all hardened and it made like one solid piece. You have to break it apart, right? We don't just leave it the big piece. So we're going from 6 sides to 36 sides. So that is what we mean by increasing surface area, okay? So for this one, what effect is the surface area? It increases your, sorry, you want to crush or grind the bigger chunks, okay? Oopsie, I cannot write today. Chunks to make more areas for water to collide. So what I mean by collide with it, if you remember our little video where we watched how water breaks apart our different substances, like ionic substances, water kind of comes in and surrounds them and then just pulls them away, right? So think about it. If you have 36 areas that water can get in there and tear it apart, you're better off than if you only have 6 areas. And that's kind of what we're talking about with that, okay? All right. So electrolytes, remember that an electrolyte is the thing that will conduct electricity when dissolved. So when it's in aqueous solution, okay, it conducts an electric current. because of the ions. Don't worry about being strong versus weak. I'm not going to ask you guys that, okay? Non-electrolyte does not dissociate, so you can kind of say that. Looking here, if we needed to figure out if it was an electrolyte or non-electrolyte, so once again, don't worry about strong or weak. We're just going to say electrolyte versus non. Your non-electrolytes, we're going to be distilled water, sugar, and soap. Everything else is an electrolyte. Okay? Distilled water, sugar, and soap. All right. The rest of it, you should be able to get it. Check the key later for it. I do have the key already done, so if you've already done the first questions, you're more than welcome to come check the front table right here. Okay? You guys have 2 minutes.